Open up any program you've ever used, a game, a spreadsheet, a feed. Underneath it all is the same thing. Data, lots and lots of little values. But a loose pile of values on its own is just noise. To do anything useful with them, we need structure. So we line them up, one after another, and each value gets tucked into its own slot. This is an array, a sequence of values stored side by side, and each one is reachable by a number, its index, starting from 0. The most fundamental data structure in all of computing. And almost everything else is built on top of it. Let's take it apart. Here's our array, 8 values, each in its own slot. But where do these values actually live? Down in your computer's memory. One long strip of numbered cells, stretching on and on. Your array isn't scattered around. Its values sit contiguously. One solid block, packed back to back, right here in that strip. Each cell has its own address, and every value takes the same fixed space, 4 bytes, so the addresses climb in even steps of 4. Say we want index 5. The slow way is to count there, one slot at a time. 0, 1, 2, 3, 4, 5, tedious. And the bigger the array gets, the longer this takes. But it never has to count. The address of index I is just the base address, plus I times the size of each element. Index 5, 1000, plus 5 times 4, address 1020. The computer goes straight there, one step. And this never changes, whether the array holds 8 values or 10 billion. Reaching any one of them is always a single calculation. That's constant time. Big O of 1. We've seen the one thing arrays are brilliant at, jumping to any index instantly. Index 5, right there, no searching. Constant time, big O of 1. But what if we don't know where a value is? Say we want to find the number 23. The array has no idea where it lives, so it checks 1 by 1 by 1. There it is. But worst case, the value is last, and it checks every single element. Search is linear, O of n. Now the expensive part. We want to insert a new value, 50, at index 2, but that slot is taken. So everything from there on shuffles over by 1 just to open up a gap. Only then can the new value drop in. Insert near the front, and you move almost the whole array, O of n. Delete is the same story in reverse. Take a value out, and the hole it leaves has to be filled. Everything after slides back. More shuffling, another O of n. But there's one edit array's love. Adding to the very end. Nothing comes after the last slot, so nothing has to move. You just drop it in. Constant time. So here's the scorecard for arrays. Access by index is instant, and appending to the end is basically instant too. Both constant time, but searching or inserting or deleting in the middle, every one of those is linear. O of n. That shuffling is the price arrays pay to keep everything packed tight in a row. Next time, a structure that pays a very different price, the linked list. Last episode, append got an asterisk, O of 1 star. It's time to explain what that little star is hiding. A real array reserves a fixed block of slots the moment it's created. Its capacity. This one holds 8, and right now, every slot is taken. It is completely full. So what happens when you try to append now? There is simply nowhere to put the new value. So the array does something drastic. It allocates a whole new array, twice as big, 16 slots. Then it copies every single element across, one by one. And copying all n elements is itself O of n, the expensive part. Now there's room. The new value finally drops in, and the old too small array is thrown away. So is append secretly slow? Here's the clever part. Because we double the size each time, these costly copies happen more and more rarely. Most appends are instant. The rare expensive copy, spread across all those cheap ones, averages out to a small constant. That is amortized O of 1, the asterisk. This self-growing array has a name, the dynamic array, and you've used it everywhere. Python calls it a list, Java, an array list, C++, a vector. Underneath, it's just a fixed array that quietly doubles itself whenever it runs out of room. So, the array. Values packed side by side in memory, which lets you jump to any index instantly. The catch? Inserting or deleting in the middle means shifting everything, and when it runs out of room, it doubles itself to grow. Arrays keep everything in one tight, contiguous block. But what if the values didn't have to be neighbors at all? What if each one simply pointed to the next? That's a completely different structure, the linked list, and it makes the exact opposite trade. That's next time. Thanks for watching Code for Code. If this made arrays finally click, stick around. There's a lot more to build. See you in the next one.